What you are looking at is the first real image ever taken of a black hole. This glowing ring surrounds an object that, according to string theory, may be woven from tiny vibrating strings and sheets. Black holes are among the most extreme objects in the universe. They are places where gravity becomes so strong that our two greatest theories, relativity and quantum mechanics, must work together. Understanding how they do so is one of the central challenges of modern physics. Let us begin with an analogy. Imagine you are holding a storybook, let's say The Tortoise and the Rabbit. This book contains information. Now imagine you are a god with a dial that controls gravity. As you turn up the dial, the gravity becomes so strong that the book is crushed almost to a point. This is our black hole. The pages are squeezed together and the story seems lost forever. Nature then pulls a dark curtain over the crushed book. This curtain is the event horizon. You cannot see inside, but the surface of the curtain still carries a shadow of the story. In physics, that shadow is called entropy. Our goal is to write the book so that the shadow on the curtain tells exactly the same story. At first, this seemed impossible. Then, physicists discovered a mathematical cheat code. If we freeze the book to absolute zero so its pages cannot move, the story survives the crushing process. This trick is called supersymmetry. When physicists counted the information on the horizon, it matched perfectly with what was written in the original book. This was a historic triumph and one of the first precise bridges between gravity and quantum mechanics. But real black holes are not frozen. They are hot, spinning, and chaotic. The pages should scramble, and if original story said the tortoise won, the curtain should say the rabbit won. Astonishingly, it does not. Even without supersymmetry, the story still matches. No one knows why. My research explores this mystery. Using extremization, a kind of mathematical audit, I test whether these entropy calculations are truly correct. I also study neutral black holes, which have almost no identifying labels. It is like reconstructing a book after all the bookmarks have been removed. Yet the story still emerges perfectly. The entropy matches. One clue may be spin. Like a rapidly spinning top that resists falling apart, angular momentum conservation may help the black hole preserve its information. We still don't know the mechanism, but every successful calculation suggests that deep inside the most violent objects in the universe, nature is preserving information with extraordinary precision.